All right, we're going to do part 2 of this problem now. In part 1, we started with our nonlinear system and we found the 3 equilibrium solutions. In part 2, we want to classify each of these 3 equilibrium solutions, and we do that with the local linearization or the Jacobian. The Jacobian is this matrix. It is the matrix containing the partial derivatives of the right-hand sides here. So this is our first equation. The partial derivative of this with respect to x is 2x minus 2y. And the partial derivative of this with respect to y is a negative 2x. The second equation, the partial with respect to x, is negative y squared. And the partial with respect to y is negative 2xy plus 2. So we have our Jacobian matrix. It's the matrix that contains all 4 of the first order partial derivatives of the right-hand sides on our system of differential equations. With the Jacobian, we now want to evaluate the Jacobian at one of our equilibrium points. So let's start with 0, 0. We'll classify that first if we can. Jacobian at 0, 0. So I'm plugging in 0 for x and 0 for y here, and most of these things turn into zeros. So I end up with 0, 0, 0, 2. Now the idea of this method is that this nonlinear system is going to behave like this linear system in the neighborhood of 0, 0. So if I'm close to 0, 0, my nonlinear system will do what this linear system does. And I know how to find out what the linear system does. I use the trace determinant plane. So the trace is 2 and the determinant is 0. So in the trace determinant plane, we are somewhere right here. Trace is 2, determinant is 0. Now that's on a boundary. And if we end up on a boundary, because this is an approximation, as you zero in on the point, you have behavior that's like this system, but not exactly this system. So if we're on a boundary, we're not really certain how to classify this. We might have an unstable node, or we might have an unstable saddle. So it's unclassifiable. And that would be an answer for a homework, right? Unclassifiable, we can't do it with this technique. We do know that it's unstable. It's either an unstable saddle or an unstable node. We just don't know which one for sure, or something in between. But it's unstable, and that's as far as we can go on that. But let's look at the next equilibrium solution. Let's look at 2, 1. So the Jacobian at 2, 1, I'm putting in 2 for x and 1 for y. So 2 times 2 is 4, minus 2 gives me a 2. 2 times negative 2 is negative 4. I have 1 for y, so this is 1 squared is 1, negative of that is negative 1. And then let's see, I have a negative 2 times 1, which is negative 4 plus 2. This is going to be a negative 2 here. So this is the Jacobian at the 2, 1 equilibrium solution. Now I want to classify this. So tau is 0, and delta is, let's see, negative 4 minus negative 4 times negative 1, so negative 8. With delta being negative, we have a saddle. And that's not about border point. It's everything down below the tau axis is a saddle. So this isn't a boundary between two things here. It's just a saddle. And we have classified successfully this equilibrium solution. There's one left, negative 2, negative 1. We put in x equals negative 2 and y equals negative 1. We are going to get negative 2. X is negative 2, so this is a positive 4. Y is negative 1. Negative 1 squared is positive 1. And then this negative means negative 1 here. And finally, let's see, negative 2 times negative 2 times negative 1. It's going to be a negative 4 plus 2 is negative 2. So the trace is minus 4. The determinant is, looks like 4 minus the negative 4 is 8. So trace is negative 4, delta is 8. We're somewhere in this quadrant. It's the stable side of things on the trace determinant plane. We have to look at tau squared minus 4 delta to decide what we have. So that is 16 minus 32. That is negative. That means the delta has more weight than the tau squared. means we're up higher in delta, we are above the parabola. So we actually are somewhere in here, and we have a stable spiral. So we have used the Jacobian, the local linearization, to classify each of the three equilibrium solutions that we had. We find the Jacobian, we evaluate the Jacobian at the equilibrium solution, and then we use the trace determinant plane to make our classification. Sometimes we end up on a boundary and we have to say, we can't classify that. We'd have to look at a plot of the phase portrait or something else in order to get our classification. But we were able to classify the other two. We have an unstable solution and a stable solution at the other two equilibrium points.